Okay, welcome everyone to today's CDAC webinar. Today I have the privilege of introducing Suxing Hu from the Laboratory for Laser Energetics at the University of Rochester. Suxing is the distinguished scientist and group leader of the Theoretical High Energy Density Physics group there. Suxing earned his PhD in physics, Chinese Academy of Sciences at the Shanghai Institute for Optics and Fine Mechanics. After graduation, he received a Humboldt Fellowship and continued his work at the University of Freiburg and at the Max Born Institute in Berlin. Suxing was a postdoc at the University of Nebraska Lincoln before becoming a director's postdoc fellow at Los Alamos National Laboratory, and then joined LLE as a scientist in 2006, becoming a senior scientist in 2013 and a distinguished scientist in 2019. Suxing has been amazingly prolific over the recent years, particularly in the last few years, and today he's going to give us an update, I believe, on some of his simulations approaching improved techniques and higher accuracy. So over to you, Suxing. Thank you for joining this webinar.
Thank you very much, Ross, for this great opportunity to talk here. Let me just trying to share my screen here. I hope everyone can see my screen. Let me just make it a full screen. Is that okay to everyone? Looks like.
Perfect. Thank you.
Thank you very much, Ross, for the nice introduction. Thank you everyone to tune in. I just realized this is one day after the long night election. Hopefully everyone get a recovery, some sort of. So let's get away from politics, talking a little bit of, discuss a little bit of physics. So today, as Ross introduced, I will tell you a little bit what work we are doing to try to improve the accuracy for simulating warm dense matter. So let's get going. This is my collaborators today. Most of the work are from Katie Heilig and Shui Zhang and Dalen Dukan and Valentin Karisev, who are in our group are doing all sorts of technology or maybe a methodology development. The whole goal is trying to understand how matter behaves at extreme conditions. I also have collaborated with the groups mostly around the world. Let me just give you a little bit introduction. What this group is about: high energy density physics theory group at the Laboratory for Laser Energetics at the University of Rochester. Currently, we have like 7 scientists working with 9 PhD students, 6 undergraduate students. So we are roughly like 22 people, a relatively small team, trying to understand how matter behaves at extreme condition.
Hello, Thomas.
So are there any questions there? No?
Go ahead.
Okay, if not, then so all the group is working on all aspects of high energy density physics. That's what we call. Let me just give you the brief outline of this talk. I don't know how this audience are familiar with warm dense matter, but in any case, I will give you a brief introduction. What's this WDM and why do we care about it? And also touch a little bit what are the methods we are using to simulate or to understand this system, like a warm dense matter. Then I will give 3 examples what we are working on, trying to get a better understanding how a different system ranges from MgO to titanium carbide and CO2 under extreme condition or warm dense matter condition. Hopefully at the end I will give a short summary. Let's dive in. What's the warm dense matter? By the way, if you have any questions, you can speak up, interrupt me, I don't mind. Let's just get to the discussion more interactively, if you will. Okay, what is warm dense matter? I put a picture here is in the density and temperature plan. We going from a very low temperature all the way up to 10 to 9, a billion Kelvin, and density from a little bit below 1 gram per cc all the way to 1 million. And on this plan, as you can see, this warm dense matter is in this regime, over regime. And if you want to make a comparison, the traditional condensed matter is sitting in this small corner, which is below 10 gram per cc and solid liquid. Mostly like if you traditional condensed matter is in a solid, so you're talking about a temperature is less than a few thousand Kelvin, and the density is around a few gram per cc. But there's a huge space in the density and temperature plan. For example, over the universe, you can have matters in really very, very high densities, as high as can be even over millions of gram per centimeter cubic, and the temperatures can range from hundreds of Kelvin all the way to millions of Kelvin. We call this as extreme matter. But if you walk towards the high temperature, a little bit high temperature, that's the regime we call warm dense matter. So you are in the regime between gram per cc and up to thousands of gram per cc. But if you keep walking towards a high temperature, that's a classical plasma. I was warned by Ross saying, well, maybe not in that high temperature regime, but instead of some of the warm dense matter or even relatively low temperature could be some overlap with the interest from this audience. So the question is, why do we need to care about this so-called warm dense matter? Well, there are challenges, right? Basically, the classical plasma theory dealing with this left up corner cannot directly apply to this regime. And the condensed matter theories in this low temperature regime will find it difficult to apply to this middle temperature regime. That's a warm dense matter regime. So in terms of theoretical aspect, this is a challenge regime, how to describe the system in an efficient way. In the practical application, of course, for those people knowing that the laboratory for laser energetics is working on laser direct drive inertial confinement fusion, that's called ICF. So what I'm showing you here in this orange dashed line is the path of the ICF. So apparently you can see this ICF and protein shell path is passing through this regime. So we do have a need to understand better, like equation of state, opacities, or transport properties in this regime. So talking about ICF, let me just give you a clips which shows what every day we are shooting a target on this Omega laser facility at the University of Rochester. Basically, this is roughly 1 millimeter diameter target. We shine laser on this system, and what you will see from this hydrodynamic simulation is you basically squeeze this target and get a high convergence. And what you will see is this, lots of this material is packed into a small and small volume, and you apparently can get a high density. So as I said, the warm dense matter is the conditions of this shell during its inflate inward. That's why we need to understand that better, how this material property should look like. And in terms of the goal for the ICF, of course, recent years on NIF, this collaboration already demonstrated that you can get ignition, which means the output energy can be well larger than the input, which we hope one day that could make a clean energy for the society. So this understanding this warm dense matter is a key issue for the ICF better understanding or reliably design ICF target. That's why this whole group, our group, exists in this laboratory for laser energetics. So as I said, by using this spherical approaching or spherical convergence, one can create and probe super dense matter. I give some example here, right? This is some of the recent work we did. We use the omega laser. Again, I casted these conditions on this temperature and density plane. And this purple circle here is what we explored both theoretically or computationally and also experimentally. What I'm showing you here in the middle plane is if you just use the density function theory, say, well, I have like a material like a 1000 gram per cc, what can happen? And these calculations demonstrated that some weird things can happen. What's the weird thing? Well, the weird thing is if you do have such a very, very dense matter, basically different species will see each other in their neighborhood. And the electrons, even some bounded electrons, they just cannot really distinguish which ions is their parent ion. So what's the consequence of that? Well, the consequence is that you will have something we call the interspecies transition. In terms of like a spectroscopy, you will see some new emission lines to show up. And this is just purely from a computational point of view. That's a DFT prediction. And of course, we have not reached to that high density yet, but we, in the past 2 or 3 years, we do put experiment and trying to get some measurement in the tens of gram per cc or even up to maybe 50, even 100 gram per cc density. What we saw is that, yes, indeed, the DFT calculation seems recover this spectroscopy feature pretty closely than some of these traditional models. However, today, I will not talking about this. My talk will not focusing on that because, as I said, this is too dense and too hot. We're talking about here is mini Kelvin. But instead, we're focusing today, my talk will be in this blue square regime, which is the low temperature limit of the warm dense matter. So again, the whole idea is focusing on what kind of technique we can make a progress on predict accurately the material properties. So let's just get into the second part, which is touch a little bit of the DFT or some recent development of the DFT. The sumo DFT. Okay, so let's touch a little bit of the basis. What are high energies? To us, it's just a quantum many-body system, right? Picture, which is in such a box or whatever your simulation box, or you're in reality, if you just in experiment, you just zoom into inside your sample, and the material is constitutes by the electron and the ions in this energy level, right? So all the electrons will interact with all the other electron, ions will also interact. And again, you can write down the Schrödinger equation perfectly. You know each term. This is an interesting quote by Paul Dirac back almost 100 years ago, saying, well, it's done. We know the equation, but the trouble is how you can absolutely solve the wave function. And to tell you the truth, is even after 100 years, we can only absolutely accurately exactly solve that only up to 3 electrons so far. So density function theory is the most popular working horse in this field. Of course, there was other ways, such as like a quantum Monte Carlo, but each of the methods has their own advantages or disadvantages. Back to the density function theory, which is invented back to the middle of 1960s, it is a mean field method. What it does is it just reduces the 3n dimension problem, right? If you think about it, you have n electrons in your system. Each electrons have a 3-dimensional degree of freedom, and you will end up with a 3n dimension problem. As we just said, that's not solvable. But the DFT does is it just reduces that 3n dimension problem to an n 3-dimension problem that we can solve numerically. To give you an idea what this called the Hohenberg-Kohn theorem, it tells you is that the Schrödinger picture that can be equivalent with you picking any electrons, and all the other electrons interaction can be used such a mean potential to describe. And it guarantees the electron densities you get from the Schrödinger picture should exactly equal this DFT picture, right? So then everything is wrapped into this called exchange correlation function. So at the end, we end up with this called Kohn-Sham equation. As you can see, that's basically look like your normal quantum mechanics textbook tell you a typical Schrödinger type equation for a single particle. However, here you have the effective potential, which is depending on your wave function or the wave function square. That's depending on the density. So at the end, this is a nonlinear Schrödinger equation, and you will need to solve that for many of the energy bands. And again, the only approximation you needed to do is this called the exchange correlation function. So what you do is with this two, you combine with the molecular dynamics. You can simulate your system and watch how the system will evolve in time, right? That's what we call the QMD simulation. And to give you, most people knew this, but in case the basic idea is for each selected ion configuration, you use the DFT serve what's the electron density. Remember, the DFT is you basically give up the total many body electron wave function. The only thing is you say, well, I just need to find the electron density of the whole system, right? Once you use that electron density, you can get your electronic force acting on each of the ions. Then that will take it either a classical or a quantum way to move your ions. Then you get a next snapshots or next configuration, and that can keep going on. This will tell you how the system evolve in time. So I have a small clip here to show you is if you throw the atoms or your material in the box, periodic boundary condition is applied, and this is how the electron density will look like inside the box. That can tell you the quantities you want to know. Okay, so back to this part, the DFT, the approximation, so-called the exchange correlation function. And for a long time, no one really got what this part should be until some heroic effort by David Sipline and the co-authors. They use a QMC figure out what's the exchange correlation function for electron gas. And based on that, in the early 1980s or the 1960s, the people can come up with the exchange correlation function. Every time I look at this, I was so amazed how popular this exchange correlation function, for example, give this so-called PBE here. This single paper on PRL got almost like 200,000 citations. And this is the people, once this get figured out, and this is how Kohn won the Nobel Prize for quantum chemistry back in the end of 1990s. So anyway, so for DFT, this exchange correlation is a key to determine how accurate is your DFT calculation compared with the experiment or with reality. So I give a picture here. In our group, we're trying to develop a temperature-dependent exchange correlation function, and this effort is led by Valentin Karisev. Give his picture here. Let me just give you a little bit of background. Why do we need it? Why do we need it? The temperature dependent. So I'm showing you here in this left schematic, and it shows how the exchange correlation function, or this is the so-called Jacob's ladder, and it tells you you can use a different approximation. This is, by the way, this is traditional condensed matter and the quantum chemistry people are doing, which is the lowest level is the Hartree-Fock, and the next level is the LDA's local density approximation, which is this exchange is only dependent on your local electron density. And the next level is the GGA, what's called the generalized the gradient approximation. And this is how many of the levels you can go. And if you go up on the level, your exchange correlation function will get more and more complicated. But meanwhile, the accuracy will get better and better. Of course, for quantum chemistry, they love to get it to a very high level. Of course, the price you pay is, of course, the computation complexity or computational time cost will be will be high. But what's the problem if you just directly take this one to apply to warm dense matter? The problem is that all the functions developed in the 1980s, 90s, or early 20s, they are not temperature dependent. And you can understand why, because condensed matter or quantum chemistry, they don't care about the 10,000 Kelvin or 5,000 Kelvin. Even 5,000 Kelvin, most of the material will melt, right? You will get a liquid. That's not interesting to them. So from all of these exchange correlation functions, they are temperature independent. So there was low explicit temperature dependency there. But for warm dense matter, you really needed to think about it. Wow, how the temperature will change this XC function. So in our group, Valentin is leading on that, and Katie Halleck is joining the effort, and we will make a temperature dependent going up. Now let me just give you some example why we need to do this and what kind of consequence it will give us. So in the past 2 years, we developed a multi-GGI level of exchange correlation function. Remember, we also work at different level. We have an LDI level, which was developed back to 2014. Again, this is the Davis Stiplin's group after they make this finite temperature electron gas simulations, and this is really promoted this whole development of the temperature dependent exchange correlation function. So we have a temperature dependent LDI and GGI, and also the meta GGI and the hybrid. So we're working towards the more and more accurate and the temperature dependent. Let me just give you an example quickly here. This is like a helium system. What I plotted here is the relative error of the total pressure compared with the path integral Monte Carlo simulation. We are plotting this pressure difference between the DFT calculation and PMC calculation, right, as a function of the mass density. Okay, at this specific temperature is something like 10 eV. What you can see is if you use PBE, and you see you get a 5 or 6% difference. For most applications, you say, well, that's fine. Results, you wish to put the right two lines. One is the dashed right that down to near 1%, and the meta GGI level. So that can really make a difference. For the right panel show you this, it's a conductivity calculation. When you use this temperature dependent one, alumina at a 10,000 Kelvin temperature, it's moving towards the right direction. You get a better agreement with the experiment. So this one more example here. This is the metallization of the polystyrene. In Rochester, we material we used for the target. So the metallization launched a shock, and we did some experiment on Omega. This is back to 1510. To measure the visor measurement of reflectivity in the from the front of the shock. Right? So for a long time, people use PBE, including myself, we get a wrong answer. You see the reflectivity twin on. If you use a PBE, it will twin on at a much low pressure compared with the experiment. And the student Roati and took this new temperature-dependent exchange correlation functions, which is the red line, and we eventually closed that understanding gap. And basically, it tells you is that if you use a not accurate exchange correlation function like a PBE, and you will predict this molecule chains in the plastic will break it up much at a much low pressure. So in reality, this chance or this carbon chance will exist at a relatively high pressure. That's why you will see is the system will become metallized at a later high pressure instead of the PBE predicted low pressure. So we're pretty happy that can make some difference. And there was one more example. This is Katie's recent work, and she is trying to develop this true meta GGI level of they call finite temperature scan function. And this is what she applied this function to silicon dioxide. And what this picture shows is what we call the cold curve, which is a pressure as a function of the volume. And when you get to a high density going this way, you will see this, you will get a high pressure, of course. This is at a zero temperature. But what Katie showing here is this scan and this finite temperature scan can give you a based agreement with the experiment measurement, compared with this low level PBE or IODI, or even anyway. So this is zero temperature. But what we're trying to do is even the finite temperature, when you get it to the zero temperature limit, it should recover this called the scan, which give you a better understanding or a better agreement with the experiment. And the right panel shows you if you apply a temperature to the system, right? Temperature here is like hundreds of thousands, or maybe from tens of thousands to hundreds of thousands Kelvin. And what you see is the difference between these predictions with the PBE. As you can see, this difference, this pressure difference, can be as high as like 30–40%. Of course, depending on the temperature range. So this give us another example. Say, well, we are now wasting time develop something no effect. So we are pretty happy. This effort does give us some confidence to better simulate a warm dense matter. So before I go, let me stop here. If there was any questions you may ask at this point. Otherwise, I will move on. Okay. So let me just give you 3 more focused study about this warm dense matter business. The first one is the high pressure phase of the MgO. This material is important for planetary science, or even for HED experiment, because it's a potential window material for dynamic compression experiment. So what is this picture? By the way, this slide is leading on the work we are doing for this project. what is showing you here on this picture is there was a famous phase transition for this material from this called B1 phase to B2 phase. And this picture show you here is all sorts of DFT predictions. As you can see, they are spread all the way. Even for the zero temperatures here all the way to 510 GPI. And the boundary can be even more spread if you go to like a finite temperature. So what Sui is trying to do is say, well, how about we combine with a QMC method, combine with the DFT or DFT-based QMD calculation. So see if we can pin down this transition boundary. So what he did is that to use a QMC and to figure out the cold curve. Okay, cold curve is at zero temperature. He figured out what's the energy as a function of the volume. Then what he did is say, well, use that. You basically can identify which exchange correlation function give you the best results. Right? Then, by the identify the exchange correlation function, he used that to do the QMD calculation. Why do you need a QMD calculation? Because in order to figure out the phase transition boundary, you need to know the free energy of the system at these two phases. Right? So that one is like, so total free energy is the cold curve plus the electron sumo and plus the ionic sumo. So he used the Corsi harmonics plus the sumo dynamic integration. You can get the ion sumo. By the way, the electronic sumo, you can get it directly from the DFT calculation. So by combining this technique, he can figure out the scan function and also this co-hybrid co-HSE function can give you the best agree results. Agree in a good agreement with the QMC calculation. And the PBSO, that's like a 3 exchange correlation function, give you the good results. Remember, the scan is also, I just show you from Katie's work, that also give you a good results for the SiO2 system. So then Sui is using the base identified functions and they did the QMD calculation and combine this together, and he can figure out this phase transition boundary. One good thing about this is now you can see if you align the previous experiment together, and this seems to suggest this temperature value here is really aligned with the phase transition boundary. Interesting enough is a very recent experiment with the XRD seems really confirmed the phase transition boundary at this 10,000 Kelvin regime is really truly the B1, B2 phase. Showing you here is this XRD shows I think the green here is a B1 phase, and the red here is a B2 phase, and you have this open circle here is the B1, B2 mixed phase together, and you can see that aligns pretty well with Sui's IFQMC plus the QMD determined boundary. So that gives you an idea how how this improve this methodology, we can get a better understanding of phase transitions. Now let me move on to the next subtopic here. I think recently in the community there are lots of interesting about the CC bonding and the diamond formation in a carbon-containing materials under extreme condition. Give you an example is this. I listened to last year Nature Communication paper. They study hydrocarbon, and they also have experiments showing that it looks like any carbon-rich material under compression, you may get diamond out of the system. But so far, seems we are still not fully understand what's the reaction pathway or how the system get there. Also like if you have like a CO2 system, that might also possibly get a carbon precipitation if you squeeze them with some additional catalyst element or some other transition methods might also do the trick. So to understand how the chemistry happen is the focus of Katie's project here. So what she was picking is this system called titanium carbide. This is a 50-50 carbon concentration. Why this system? It looks like in Japan there was some XRD experiment. It looks like they have some preliminary results showing that they do see some diamond formation signature, but they are not 100% sure is that diamond or is that diamond like carbon bonding. So this is a system simple enough. You just have two elements, and Katie took on this system and they're trying to understand under high pressure and relatively high temperature too, and how the system will respond. So to give you some idea, this titanium carbide system, there was a predicted transition happening at like 140 GPa. Below 140 GPa, you have this FM3M system or structure, which is look like this. But above 140 GPa, you have a CM structure, and you can see it has a zigzag carbon layer sandwich with the titanium layers. So of course, this high pressure phase looks like it will give like a strong carbon-carbon bonding already. So one thing is that what this system will facilitate carbon formation. Of course, Katie did a study and trying to see indeed this carbon-carbon bonding is a strong, very strong carbon CC bonding. So what she's shown here is like if you calculate this called ICUHP, which is integrated crystal orbital Hamilton population calculation, which is it's a metric showing you how the bonding, how strong is the bonding, right? So you if this number is high, FM3M structures, you can see the titanium carbon bonding. The TIC is the highest bonding bonds. But when you get it to this CM structures, you can see the CC bonding become extremely stronger. If you look, this number is like 4 times bigger than the titanium carbon bonding. So what that tells us? Well, it tells us even at a solid, this titanium carbon structure already has this strong CC bonding. So then the question is, would that be a precondition for a favorable diamond formation? So of course, when you need a diamond formation, one of the natural thinking is that you need to melt in the system first, right? Because if you don't melt in the system, they will lock in space. The naive idea is once you melt in the system, the titanium atoms might move away, right? They might just melt, they will fluid. They will move away, make a space for the carbon to find the other carbons, right? So the first thing is to see how, let's just make this system melting and to see what could happen, right? So what Katie did is to use this so-called heating until it melts method, right? Basically, you do a QMD simulations, you just raise up the temperature and see how the system change, right? So what a surprise he saw is that she needs to increase the temperature well over 80,000 Kelvin to melt the system. So why this is so surprise? Because if you have a well less than the 80,000, right? Even when you have a pure diamond system, the melting temperature is 1,006 than this 80,000 Kelvin. So this system already give us a surprise. It's hard to melt, right? Another surprise she found is that even the system is melted. For example, the right panel showing you here at 80,750 Kelvin, and you can still see the carbons. They are not totally become fluid yet. They become a chain, right? So if you just take a look at the rightmost panel, it shows you the G of R, which is a pair correlation function. And you see the titanium correlation function at like over 9,000 Kelvin, you see they will like pretty much like a fluid, like, because the force, the value just like filled up. And this just simple means titanium become a liquid. And also the titanium carbon pair correlation function also washed out here. But if you look at carbon, first of all, this peak does not move much, and the magnitude does not change much. That already tell you this carbon chain is still persistent in such a melting system. So this is an interesting system. First of all, it's hard to melt, and even it's melting, and the carbon chain still persisting. So of course, when you just do such a direct QMD calculation, it's still very hard to really identify if a diamond can form because the whole system is so small. And when Katie just calculated correlation numbers, and most of the carbon bonds give you correlation number from 1 to 3. Remember, the diamond is correlation number needed to be 4. So we don't see that here. Even this is hundreds of atoms in the simulation box. But again, it's still too small for nucleation to happen or to be better simulated. So the plan is to use such a QMD simulations to train a trustable or reliable interparticle interatomic potentials. Then you can use the machine learning potential to do a large scale simulation with millions of atoms. That might be possible to see if nucleation or if a diamond nucleation can show up in such a system or not. That's the next step she's going to do. Okay, let me see if I have last a few minutes. Let me just wrap this up with the last piece, which is the CO2 study. CO2 is for people who did a study on CO2. Is the carbon dioxide is a very unique system. It's very stable. So you can compress the CO2 like hundreds of GPI. They will maintain like a molecular fluid. So I was just sitting in my office. I said, well, the CO2, of course, it's a big deal to the climate change and everything. So I was saying, well, is that any possibility? Is there any possibility one can destroy the CO2 by using pressure as a tool? So Dalen is a new graduate student working with me, and we said, well, let's just take a CO2 and squeeze it, and heat it and squeeze it. Let's see how things change. Indeed, CO2 is very stable, no matter how strong you heat. Of course, up to a few thousand Kelvin, they will maintain like a CO2 or maybe polymer become a polymer. But they are not completely destroying if you have like less than 5,000 Kelvin. So I said, well, what about if we just add in some transition matter? So the first example Dalen did is saying, well, if we just add in some rhenium atom into the system, and the surprise he saw is that when you have such a transition matter in the system, and the QMD simulation indeed is showing you that CO2 gets decomposed. Okay? So what's the signature? Well, the signature, of course, if you just look at the pair correlation function, and the CO peak is like suddenly drops quite a lot, and meanwhile you see the CC, right? At the very beginning, you don't see a CC peak at less than 2 angstrom, but when your simulation keep going to a picoseconds, and you see the CC bonding start to show up. So it tells you the CO2 gets really destroyed. So what he did is he just counted the molecules in the system, and indeed he saw the number of the CO2 molecules drops, and he also see the CC bonds increase. Interesting enough is that he did the same thing for say, well, not a 20 GPI, not a 45 GPI. If I just do a half GPI, but 4,000 Kelvin, what happened? Yes, indeed, you can still destroy CO2, but you don't have a CC bonding for half GPI. And one more interesting finding is that he also did this quench. So what he did is he took this QMD at 4,000 Kelvin, right, with the rhenium in there. Remember, this is CO2 already dissociated. Then he just run the QMD and say, well, if I just keep low my temperature, what happened to the system, right? Back to a room temperature. And it turns out, since this reaction is irreversible, what it tells us is once the rhenium facilitates this dissociation of the CO2 molecule at this high temperature and high pressure, And even you quench that down to room temperature, and the system, the CO2 does not come back. So that's a good sign. It means you will, if you do this way, you will permanently destroy CO2. Okay. So the last bit, what he did is, it looks like this kind of behavior not only happen for rhenium, but other transition metal like manganese and also like iron, even silicon. If you put a silicon in such a system, it will do the same trick. It will facilitate the decomposition of CO2. And again, back to the diamond formation possibility. If you look at his GeoVar plot, it shows the CC bonding it's very much close to the 1.5 angstrom, which is almost exactly at the diamond CC, the bond distance. So that gives us some ideas that, well, this is so close to the diamond bond distance, because in any case, at this high pressure, diamond is the stable phase for a pure carbon system. So, but the bottom line is, in order to see that happen again, this is a similar story as Katie's work is, you need to train this in potential for large scale simulations. So this is the second part. He's going to continue with this story. He got this paper published on PRB early this year, and next stage is to see if really diamond can be nucleated from such a system. So I'm running out of time. Let me just try to stop here. And what the future is, we are going to do is, with this better DFT simulation tools, we need to go bigger system and the longest simulation scale to get a certain aspect of the warm dense matter system a better understanding. With that, I thank you for your attention.
Thanks, Suxing, for a very interesting talk.
Thank you.
Last three examples were fascinating. If you would like to ask questions or make comments, simply unmute yourself, raise your hand, or put your comment or question in the chat. Maybe I'll start with the last example. Did you try temperature quenching at lower pressures with all this done at 45 GPa?
Yes, this one is done at a 45 GPa. Then you just do, I think you do a NV. What you change is the temperature. So even at a room temperature, I guess the system is still like probably like a little bit less than 45 GPa.
Yeah.
Down to a 20 GPa or so. So I remember Dalen also did something even like a half GPa. You could quench that down, and that also show the CO2 no longer coming back, although you don't see much of the CC bonding.
Yeah. At these pressures, you can also simply polymerize CO2, right? You can make a polymeric form. And there was some indication from calculations, I believe Juliet Gawley did a long time ago, that suggested that you could catalyze that to lower pressures, make the reaction occur or the transformation occur at lower pressures with a metal catalyst. So I'm wondering if you see any polymerization of the CO2, not just diamond formation or CP bonding.
Yeah, that's a good point. I don't think we see any polymerization. Probably, I'm not sure, but it looks like at this temperature is pretty much too high for the polymers to exist. But probably if you lower the temperature something like a 2000 Kelvin, might be possible the CO2 polymerization will show up first. By the way, this is the whole is a liquid, but when dialing do this at the 4,000 Kelvin. Yeah, that's a good point. Probably 2,000 Kelvin you can polymerize the CO2. But our thinking is that when you have this catalyzed atom there, you want the system in liquid to kind of like facilitate enough of the reaction or easy to react.
Yeah, yeah.
Yeah.
Questions, comments? The work on titanium carbide is also very interesting. I'm very surprised to see these strong carbon-carbon bonds at very high temperatures, as you point out. So that's really pretty intriguing.
Yes, I mean this one is really a surprise when Katie, I think Katie is on this call too. Yeah, when Katie is shown this, say, well, with so high temperature, this carbon still maintain chain there. By the way, Katie, if I remember correct, Katie used it to be also a CDAC postdoc there, right, Katie?
Yeah. This is a familiar webinar to be attending.
Okay, yeah. Can you say something, yeah, about this? Is this also a surprise to you, right?
Yeah, for sure. I definitely started my heat until melt calculations at much lower temperatures and kept going, well, still not melted yet. So of course there's always a possibility that this is an overestimate of the melting case, but I think what's really impressive is the persistence of this carbon-carbon interactions. One thing that I haven't gotten to look at in any great detail is sort of the duration of how long the carbon-carbon interactions, like their lifetime. But that's also something that I think will be better examined with a larger system size.
Yeah. I think for the CO2 one, Dalen did this like a tenth of a picosecond, even something like over 10 picosecond. This carbon chains looks like it's maintained there, floating around. But to me, it seems how these carbon chains will find their way to form a diamond. It's so intriguing to me. It was like, for example, if you have a titanium, right, relatively large atoms, they will occupy this space. And how, I mean, in my mind is how this titanium atoms will make a space for the carbons to stick with them together. It's just beyond my my comprehension for now. But nature will find their way, I guess.
Well, and in this case, the crystal structure gives it a nice little jump start. They're already in zigzag chains.
That's true.
Whereas you wonder some other carbide materials won't necessarily have that.
Right.
That's right. Yep. Yeah. So yeah. I mean, it looks like a high pressure physics. It's seems to me it's a everywhere is a surprise if you look into it.
Okay, very good. Any more comments, questions? Well, thanks very much for this very interesting talk. Thank you for touching on the sort of the cooler regime of warm dense matter where materials properties really make a difference. So very nice work and congratulations to all of you at LE. This is really
Thank you very much, Ross. Yeah, thank you everyone.
Okay, thank you for joining us. Bye-bye.
Okay, bye bye now.